Hi and welcome to another strings lesson. This lesson's topic is the REP prefixes. Objectives of this lesson. We will study the instructions SCAS and compare S. We will also learn about the prefixes REP, REP-Z and REP-NZ. Let's begin with an example. We want to clear an array of bytes, which means that we want to zero all the bytes in a given array. Let's begin with the declaration. We can see here a declaration of an array called myArray of type bytes, which is of size rlen. It has exactly rlen bytes. We want to zero all those bytes. The simple way to do it would be to use the stosb instruction inside the loop. We first load edi with myr. Next, we load ecx with rlen, which is the size of the array in bytes. And then we zero al. We are going to use this al equals 0 to zero all the array myArray. Basically, inside this loop, the only instruction that does real job is stosb. Stosb is going to store the value of al into the location pointed by edi. This loop is going to go over all the places in memory which belong to myArray, and it is going to zero every one of them. An important thing to see here is that this doesn't work very well if rlen equals 0. Well, maybe I'm a bit pedantic here, but this is going to be important later. So we want to solve this problem. Let's think, for example, what happens if rlen equals 0 of some strange reason. What is going to happen is that we are going to invoke this loop, and this is not what we want. In the case of rlen equals 0, I expect that nothing will happen. Maybe we should add some kind of a detour around this piece of code to make sure that it doesn't execute if rlen equals 0. And this is exactly what we do. We use a new instruction called jecxz, which is going to jump to finish if ecx is 0. I repeat again, this is an instruction that you haven't seen before. This is the first time I use it. What this instruction does is as follows. It just checks if ecx is 0, and if it does, it takes the jump. But if ecx is not 0, the jump is not taken. So we made a very simple detour, made of just one instruction. In the case of rlen equals 0, we are going to skip this loop. We will not do even one iteration. But if rlen equals 1, then we will do exactly one iteration. By the way, I want to mention what happens if rlen equals 0 in the previous example. Here, if rlen equals 0, we are going to invoke this loop 2 to the power of 32 times, which is going to be very unfortunate. You probably didn't expect this to happen. But here we are protected. If rlen equals 0, then nothing happens. Instead of all this logic, we could use the REP prefix. It looks like this. REP stosd. We combine this prefix, REP, with the instruction stosd. Basically, what this prefix is going to do is as follows. It is going to execute the stosb instruction exactly ecx times, which is just what we did in the previous example. But you have to admit that this is much cleaner and shorter. So, as we have mentioned, this code will behave exactly like the previous one. They are equivalent. Let's talk about the REP prefix in a more detailed fashion. It looks like this: rep and then a string instruction. This is the general syntax. I want to mention that rep works with a few predefined instructions. For example, stos, load s, move s, and some other two instructions that we are going to see here. You might have wondered if you can add the rep prefix to any instruction. This is not the case. Rep works only with a few instructions. Basically what rep does is to repeat the string instruction, which is here, ECX times. And that's all. In the end of the execution, ECX will become 0. You can think about it just like we were decreasing in some kind of a loop. This is actually what rep does. It just decreases ECX until it is 0, and then it knows that it should finish. If at this point you can read assembly better than English, then this might be helpful for you. This is the equivalent of using the rep prefix. As we can see here, we have one loop which simply iterates the string instruction. It invokes it in every iteration. And we also add this 0 protection to make sure that if ECX is 0, we don't accidentally do this loop 2 to the 32 times, which will be unfortunate. Some examples of the rep prefix. Rep stos b, which we have just seen, is great for initializing an array. If you want to initialize an array with zeros, for example, or maybe with some other byte, you can even initialize an array with d words if you use rep stos d, for example. Another example is rep moves d, which could be used to copy data. Let's talk about this example. We want to copy an array. Here we declared two arrays. One is called source array and the other one dest array. Both of them are of type bytes, and both of them are of size rlen. Let's assume that source r contains something meaningful, and basically we don't care what is inside dest r because we are going to copy things into dest r. This is how it's going to work. We first load source r into ESI, then dest r into EDI, and the number rlen into ECX. This number indicates the size of the array, or maybe it indicates the amount of repetitions that we are going to do. Finally, we use the rep moves b combination, which is going to repeat the moves b instruction many times. Let's recall what is going to happen. We actually do ECX times, copy one byte from ESI to EDI, and then we increase ESI and EDI exactly by one byte. I remind you that we assume here that the direction flag is of value 0. This is why ESI and EDI are increased and not decreased. This is the default case for the direction flag. We usually assume that the direction flag is of value 0. Let's move on with the scas instruction. Scas is also known as scan string, and it can really help you find something inside a string. It has some different forms. The first form is called scas-b, where b stands for byte. This instruction compares AL with the byte at address EDI in memory. It then sets the flags accordingly. Then immediately it advances EDI 1 byte according to the direction flag. If the direction flag is 0, then EDI is increased by 1 byte. However, if the direction flag is 1, then EDI is decreased by 1 byte. I want to discuss for a moment what set flags accordingly means. It actually means that we compare AL with this value, the byte at location EDI, and the flags are set just like they would have been set if we used the CMP instruction, the compare instruction. In other words, you may assume that we just subtract AL minus the byte at EDI, and the flags are just set accordingly. This means that all the relevant flags are being set. For example, this kind of subtraction could affect the sign flag, the overflow flag, the zero flag, and the carry flag. Let's look at the two other forms, which are basically the same, just for different sizes. The next one is SCASW, where W stands for word. This instruction compares AX with the word at location EDI. It then sets the flags accordingly. Finally, it advances EDI 2 bytes according to the direction flag. The last form is called SCASD, where D stands for D word. It compares EAX with the D word in location EDI at memory. It then sets the flags accordingly. Finally, it advances EDI 4 bytes according to the direction flag. Let's look at an example of using the SCAS instruction. We want to find the null terminator of a string. Let's begin with the declaration of the string. It is called A star, and it is a sys-style string, which means that it just contains some ASCII bytes, and finally a zero terminator. We can find the size of the string by looking for the zero terminator. And this is what we want to do here. We want to find the zero terminator. We begin by loading A star into EDI, followed by zeroing AL. Why we want to zero AL? Because we want to find the value 0. If we wanted to find another value, for example 3, we should have replaced this instruction with, for example, move AL 3, and then we could find the number 3 inside the string. But here we want to find the null inside the string. So we zero AL. Next, we execute the instruction SCASB inside the loop. As you can probably imagine, we just want to compare 0 with every character on the string. We want to compare the value 0 with every byte inside A star. And we want to stop the comparisons whenever we find a 0. So we can use the effect of SCASB over the 0 flag. I remind you that SCASB affects the 0 flag the same as comparing AL with the current character in the string. So if we got a match, then the loop is going to end. But if we didn't have a match, then the 0 flag is 0. And then we move on to the next iteration to compare with the next byte. Let's take a look at an equivalent code just to make sure that we understand how the SCASB instruction works. As we can see, we just replaced the SCASB instruction with those two instructions, compare and then LEA. What I claim is that SCASB is absolutely equivalent to those two instructions. As you can see, anything else is exactly the same. The only thing that we changed is we transformed this instruction, SCASB, into those two instructions, compare and LEA. We first compare AL with the byte in address EDI, and then we increase EDI by 1. You might be wondering, why use LEA when we could just use increase? This is an important question. The answer is as follows. LEA doesn't change the flags. And this is important here because we use the 0 flag from the comparison. We don't want to change the flags in this instruction. So here, J and Z corresponds to the CMP instruction. This is exactly what happens here. SCASB actually first compares AL with the byte pointed by EDI, and then it increases EDI. But you have to remember that the effect on the flags only comes from the comparison. But what if we never find the null terminator? This could happen. For example, maybe someone made a mistake and he forgot the null terminator. Or maybe you got a string from the user as input. You cannot always trust the user of your programs. Maybe the user of your program didn't supply a null terminator. Such things could happen, and we want a fail-safe mechanism to make sure that we don't just keep looking for the null terminator forever. This could crash our program. For example, if we keep searching for the null terminator beyond our own memory, the program is going to crash because we will access memory that we don't own. We begin with this code, which is prone to this problem. And we are going to improve it by adding a fail-safe mechanism. We first move the value max star into ECX. This is the first modification. Max star is going to represent the maximum size of a string that we are willing to handle. The first modification is here. Move ECX max star. Max star stands for the maximum amount of bytes that we are willing to handle, or maybe the maximum amount of bytes in a string. The next modification is here. We add those two instructions. J ECX 0 exit loop, which is going to exit if ECX equals 0. Next we have this instruction, decrease ECX. And finally we have this label, exit loop. I want to talk basically about the meaning of this change. This change is all about making sure that we don't iterate too much. We just defined earlier in the code that we don't want to do this loop more than max star times. Which means that, for example, if max star is 3, this loop will only happen 3 times. It will not iterate more than 3 times. So actually we get 2 termination conditions. The first one is 0 flag equals 1. This termination condition can be seen by this instruction, J and Z. If the 0 flag is 1, we are going to exit the loop. The second termination condition is ECX equals 0, which can be seen here. If ECX equals 0, we just jump out of the loop. Basically, we just added some instructions to make sure that we don't stay inside this loop too long, because we don't want to stay here forever. We want to make sure that either we find the null terminator or we have gone through max star bytes. This is the maximal amount of bytes that we are willing to check. We are not going to check more than max star bytes. You were probably worried that this code became too complicated. But don't worry. There is a special prefix just for this case. It is called the REP prefix. We could just replace all those instructions with one instruction, rep NZ scas B. I don't want you to be bothered with all the small details and the subtleties. I want you to understand this intuitively. We just want to find a null terminator inside a string. So first, we set this number max star and we move it into ECX. Then we load A star into EDI, and finally we pick a value that we want to find, which is in this case 0 with 0 AL. And then we ask the processor to find AL. And this is about what we say. Keep looking for the byte AL until you find it, or until you searched inside max star bytes. And if you did, stop searching. I will repeat it again. Repeat as long as you didn't find the byte AL. And also make sure that you do not repeat more than max star times. So basically there are two ways in which this compound instruction will finish. The first one is if we actually find the null terminator, and the second one is if we have already checked max star bytes, which is too much, and then we finish the instruction.